And that is synonym when you see increasing exponential is because increasing faster, no? Increasing too fast. However, not always is true this exponential because exponential growth is the increasing function, but the problem is we have a special condition. So we have, for example, we are talking about microorganism, maybe virus, that's okay, bacteria, maybe a small animal like a rabbit, mice. Yeah, a little bit you can approximation the population, no? Like exponential. The reason is clear. It's because the microorganism or small animals have enough space and have enough of food. Completely situation different happening in the human being. Human being, no increasing exponential. You see the population of the planet increasing, no. This is completely wrong. Okay, exponential is when it's inhibited. So we have no limitation. In the human being, of course, yes, we have a lot of limitation, and also I have competition. See, we have competition. Maybe one element destroy another element. So it never is exponential. But that's okay. I promise that we study in detail any functions que derive somehow for the exponential. No? Okay, so today we are doing the exponential equation. Okay. Same for me. What part is same for you? Uh, suppose exponential equation. Suppose this example one. It's equations que contain the unknown, the variable that you need to find, that you need to solve it in the exponent part. 3 minus x equal 8. Suppose this example. So some students don't understand very well and believe that this is 2 parentheses 3 minus x equal 8. No. This is 3x, 3 minus x is an exponent of the 2, right? So no, you cannot apply distributive property. No. So what is the technique that we studied? So the first technique that we studied for solving this. You try when it's possible. Sometimes it's impossible, but in this case it's possible. Manipulate both sides in order to express it using the common base. Common base. Entonces es obvio, you copy here in the corner of the piece of paper que 2 es 2. 2 to the 1 power, no? And 8 is 2 to the 3rd power. Then we can find a common base, que by the way is 2, no? Then you rewrite 2 raised to the 3 minus x and just bring down equal, instead of 8 you put 2 to the 3rd power. And this is super important, crucial moment. When you have two exponential and the base is the same, it's because the exponent is the same. And the reason is clear. It's because the exponential function is one-to-one function. Therefore, you magically, this is magic, you convert exponential equation to another equation que is not exponential, in this case, super linear equation. Es obvio que x is 0. Yes or no? Do you understand this first trivial elementary kindergarten example?
Yes.
Okay, this is the technique, the first technique we use. Find the common base. Not always is possible. Entonces, when it's impossible, we explain another more sophisticated way. Example 2. 5 raised to the 2x plus 1. This expression is exponent of the 5 equal 25. Oh, it's obvious that the common base in this case is 5, no? Because 5 and 25 is 5 squared. Then you replace, not 25 anymore. No. This is 2x plus 1, stay the same, but this is 5 squared. Now again, same situation, two exponential. Same base is because the exponent is the same. And you convert the exponential equation in one linear or quadratic, depending, no? Depending on the example, and you solve it using the algebra, you know very well. 2x is equal to minus 1, que es 1, divided by 2 both sides. Es obvio que es 1/2. And the solution is 1/2. By the way, the exponential equations is different to another equation. For example, radical equation, when you study in the chapter 1, radical equation, you need to be checking the answer in the original equation, mandatory. The reason is because a radical equation, the domain of the radical function is not all real number, it's only positive and 0. Negative number, because the square root negative number, you know, gets completely out the all real number field. Therefore, you need to check it, because sometimes in the manipulation, in the transformation for the equation, you obtain a new equation that is equivalent somehow to the original, but give me a extraneous solution. But exponential never happen. It's nice, because remember, the domain of the exponential function is all real number. So maybe you have solution positive, solution negative, solution 0, like in the first example, and it's a perfect value, right? 27 for x equal 9, x plus 2. Okay, this is the third example. The exponential equation is 27, the exponent is 4x equal 9, x plus 2. Entonces, I try to ask by myself, I can find common base or no?
Yes.
What is the common base, in your opinion?
3.
3, it's obvious. It's 3 because 27 is 3 to the third power, and 9 is 3 to the second power. And you replace. No 27 anymore. This is 3 raised to the 3 raised to the 4x. And you replace 27 like a 3 to the third power. And 9 is 3 to the second power, x plus 2. And sometimes happens that we have different level of the exponent. And you need to know perfectly the rule of the exponent that you apply in this case. Suppose you have x to the second to the third. Okay, it's x to the 6th, because the operation that you are doing in the exponent is multiplication. Exactly the same we are doing here. It's a 3 raised to the 12x. Where come from 12? 3 times 4 equal 3, 2 times parentheses, because 2 multiply everything inside the exponent is x plus 2. Okay, one more time, we have exponential, same base, therefore mandatory you separate, ignore the base, irrelevant, and focus it in the solution of this equation. Okay, it's linear equation, by the way. 12x, you apply distributive property, 2x plus 4, 2x minus 2x equal 4. This is 10 equal 4. I continue here, divided by 10 both sides, x is equal 4 or 10. You can reduce it in lowest term to 5th. Final answer. Any question? Easy, eh?
Yes.
Yeah, so far. Example 4. Example 4 is square root 3 raised to the x plus 4 equal 3 to the x. Again, I try to investigate, find the common base. What is the common base in that case? Common base. Well, 3 is 3. And radical 3 is 3 to the 1/2. Remember fraction exponent, no? Do you remember that or no? No? Yes? Yes? No? Do you remember radical exponent and radical fraction exponent? Sorry. Equivalent. Okay, Anika is a yes. Okay, so now replace. No, I put it in this way. I put using radical normally. However, I know the equivalence in between fraction exponent and radical. No? Okay, this is x plus 4. Here is 3. 2x. Okay, so now again we apply the property for the exponent. Multiplication is 3 to the 1/2 time x plus 4 equal 3 to the x. Okay, super. Same base, same exponential, therefore the expression of the exponent is the same. Okay, something like that. Well, I don't like the fraction, so you multiply the entire equation by 2 if you want to eliminate the fraction. When you multiply 2 times 1/2 is obvious que 1, and 1 is invisible. And here is 2 times x is 2x. Wow, equivalent equation without fraction. Now we solve it. 4 is equal to x minus x. And 2x minus x is x, and it's the answer. X equal 4. Cool. Let me try another. I have a lot of. Okay, one more. Example 5. We are doing an exponential equation. It's equation, new kind of equation, that contain the unknown and the exponent part. And magically, we convert to the linear equation or another equation, non-exponential, non-exponential at least. Okay, what is the common base in that case? Common base. Come on, guys. Say again?
2.
2, I agree. Because 2 is 2, and a is 2 to the third power, similar to the first problem. So 2 raised to the 1 minus 2x is equal to the third power raised to the x plus 1. You apply the rule of the exponent multiplication. We have 2, 3 times x plus 1. Okay, in that moment we have two exponential with the same base, therefore I ignore the base. I copy only the exponent equal each other. And we focus in the solution of this equation. It's super straightforward. Look, let me show you. You apply this derivative. This is 3x plus 3, no? Okay. Now I suppose that one better idea is moving 3 to the other side, because the 1 stay here, minus 3 is equal to 3x plus 2x. This is minus 2, and this is 5. X divided by 5 both sides. X is equal negative 2/5. Boom. Final answer. I don't care. The answer is all real number domains. So we can find solution, positive, negative, 0, okay, irrational, okay, real number. Yeah. No imaginary. No, this is crazy. Okay, example 6. 2/3 raised to the x is equal 9/4. What do you propose me to find the common base? What is the common base? I have no idea. There are some connection in between 2 and 4 and 3 and 9, maybe, no? Help me. Come on, guy. Participation. I appreciate so much participation. Nobody have idea? There are connection between 4 and 2, or no?
Yes.
Yeah,
And 3 and 9 too.
3 and 9 too. So 4 is 2 to the second. I copied one corner of the piece of paper. Don't worry, I don't have the full idea in my hand. However, I try to do piece by piece. And 9 is 3 to the second, no? Okay, so see, I replace. 2 is 2, 3 is 3, the exponent is the unknown, I don't have idea. However, I can write like that. This is 9 is 3 squared over 2 squared. It's okay so far? Okay, now 3, the exponent is the same as 2, so you can write like that, 3 over 2 squared. Make sense or no? Make sense or no?
Yes.
Okay, okay. So now, the problem is, in the left-hand side, we have 2 terms. In the right-hand side, we have 3 over 2. At least I can see it's reciprocal, yes or no? So you flip it, you get the same base, no? How you flip it? How you flip it? Suppose I make a decision. I don't know. This stays the same, but this I flip it because my goal, remember, is to create the same base, no? But what happened with the exponent? Stay the same or change? What action help me to flip it and the exponential? This is important detail. This is important detail. Okay, you need to know. No idea.
The same?
No. Si it's the same, no. What is the action can you flip it? Suppose you have fraction. All right, let me try to understand. Suppose we have 1/2. I want to get 2 over 1, because the action of the flip it, right? This is one exponent. So you put one exponent, we are doing nothing. So how you flip it? What exponent you put in order to flip it? Flip it. No idea. No?
I'm gonna take a guess and say 4. I'm sorry.
No.
I'm sorry, I was looking at the wrong one. I'm gonna say.
Well, you okay? Come on, but
2.
You 2, no, because 2 is 2 squared 4 and 1 squared 1. No.
So then this.
Okay, flip it is -1.
-1. Okay.
A surprise for you or no?
No, it sounds about right. I wasn't thinking, but yes, -1.
-1. When you have negative exponent, the meaning of negative exponent means reciprocal. Okay? Well, see, you raise to the -2, just you are doing two action, reciprocal and a square after, no? But in this case, obviously, -2. Yes or no? So the action to flip it is responsibility of the negative sign. Negative exponent, guys, this is important. Remember, we are studying exponential function, and the exponential function, you can, any base, suppose 2 to the 1, 2 to the second, 4, and so on, 2 to the third is 8, and suppose exponent negative, 2 to the -1, is 1/2, yes or no? And 2 to the -2 is 1 over 4, and so on. Reciprocal. Make sense?
Yes.
Okay. Now I am ready. I finish because the exponential is the same base. Okay, I create, no? And therefore, the solution is x equal -2. In the story, I finish. Okay, this example bring me a new situation, case not always happen that the base is identical, it's reciprocal, but you solving the problem using negative exponent. Suppose example 7. Example 7 is 32. Do you follow me, guys? Do you understand very well or no?
Yes.
Okay. Suppose this. I try to solve this exponential equation, but I need help. What should I do? I try to discover a common base. What is the common base? This is the problem. What is the common base?
I would say 16.
Well,
because 16 can go into 32. And then also, even though it's flip x plus 2 and x minus 2.
okay, good. Forget about the exponent for a moment.
Okay.
So I try to find the common base between 16 and 32. Oh, wait. This is 4. Anika 4. One opinion was 16. Maybe let's try to analyze. Another opinion is 4. We have another opinion. Okay, let me try 16. 16 is 16 raised to the 1 power, no? But 32, So you raise 16 to the second power, it's 200 something, no? Let me try in a calculator. 16 squared to 256. You see it's too hard, too fast, no? Increasing too fast. No. 16 no common base. And let me try 4. Well, 16 is 4 to the second power, correct. But you continue base 4 and you raise to the third power, maybe get the next, no? 1, 2, 3. It's 64. And I need 32, gets a half of this. That's a 4, no? Do you see it now?
No, yeah, it's 2.
It's 2. It's 2. Let me try. 32 is 2 to the 5th power because you multiply 5 to 2 times 2 times 2 times 2 times 2 is 32. You put in the calculator, of course. And likewise, or similarly, 16 is 2 to the 4th power. Okay, I discovered the common base is 2. The common base, the answer for that equation is 2. Is the common base. Now already you replace. That make more that made more sense. That's it. Now 32 is 2 to the 5th power. You replace by the expression that contains the common base, x plus 2. And 2 to the 4th power, you replace the exponent is 2 minus x. You don't touch the exponent. You only thing, the only action is replace 32 and 16 using the corresponding power with the common base. And now multiplication. Entonces 2, 5 times x plus 2 equal to 4 times 2 minus x. Ready. Two exponential function, same base, therefore magically happen that I ignore the base. Y I copy just the exponent, get 5x, parentheses. Don't forget the parentheses because it's part of the game. You apply this derivative property, 5x plus 10 equal 8 minus 4x. Let me try to solve for x, linear equation, exactly the same we are doing in intermediate algebra. I move 4x to the left. I'm moving 10 to the right. Opposite sign, this is 9. This is minus 2 divided by 9 both sides. X is equal to minus 2 over 9. Let me check in my paper. Yeah, that's the answer. One more example. And you help me. Example number 8, no? Yeah. Example 8. Example 8 is cubic roots. Wow, what the hell? Of 5 raised to the minus x. Ooh, negative exponent. This is confusing. Very complicated problem. 1 over 5 reciprocal. Wow. X plus 2. And my question again, what is the common base, in your opinion? I suppose que es elementary, ¿no? What is the common base? Don't complicate too much with the exponent negative. No. What is the common base que you see using your eyes?
5.
5. Let me try to do my best. In order to express it, the thing I have in the equation using the base 5. So a cubic root of 5 is equivalent to, say, 5 raised to the 1/3. Yes or no? It's a conversion, radical format, radical form to the exponent fraction. Classical. Yes or no?
Yes.
And 1/5 is a reciprocal of 5, no? Entonces 5, what exponent are you using? Here. What exponent are you using to flip it? Guys?
Negative 1/3.
Negative 1/3, no.
Or negative 1.
Negative 1 alone.
Okay.
Oh, negative 1. Cool. Okay, keep in mind, exactly the same. I record the video in Skype. Record in your mind. Negative exponent, flip it, right? Now, ready. This is equivalent to say 5 raised to the 1/3 exponent negative x is equal 5 raised to the negative 1, flip it, x plus 2. Now the rule of the exponent, different level of the exponent, multiplication. Entonces 5 is negative x over 3, I guess so, no? Multiplication by 1/3 is equivalent to divided by 3, no? And here we have x, 5, sorry, and negative 1, que is negative 1, negative x plus 2, something like that, right? Because negative 1 multiply the whole thing. If you want, you can directly doing that. But either way, now ready to exponential the same base, therefore, minus x over 3 is equal minus parenthesis x plus 2. You apply distributive property. This is minus x minus 2, no? Okay, now ready is you moving x to the left, maybe positive x minus x over 3 is equal minus 2, no? Minus 2 stay in the right hand side, no? And you, either way, you, I don't know, you combine here, it's 1 minus 1/3, get 2/3, no? It's one possibility. Oh, so you don't like fraction, you multiply the equation by 3, it's the only least common denominator, so we have 3x minus x equal minus 6. Do you understand the action, guys? Either way, guys, either way. This is 3 minus 1 is 2. Divided by 2 both sides is negative 3. Okay, another student said, no. I don't like this way, professor. I continue working in that way. Okay, no problem. You combine later. How? Well, this is 1. This is 1. Coefficient here 1 minus 1/3. Okay, LCD is 3. This is 3 minus 1. 3 divided by 3 is 1, and 1 divided by 3 is 1/3. Subtraction is 2/3. 2/3 who? 2/3 x equal minus 2. Okay, now if you want to isolate the x, you multiply by reciprocal both sides. What is the reciprocal? The reciprocal is 3 over 2. 3 over 2. Okay, and this is cancel out. Say goodbye. This is 1, because any number multiplied by is reciprocal is 1. And 2 is cancelled if you want. The answer is negative 3. I don't know what way you prefer, fraction or no fraction. Can someone tell Professor I can get in the meeting? Michael, okay, this is the problem of online class. Sometimes happen, guys. This is the disadvantage. Now next semester, the majority of the classes in person. I only have access to the chat. Wow, this is weird. Try to open again, Michael. Try to open again. Try to, so you close everything and try to click again. Because depending on the many situations, depending on the connection, depending on your computer, you know, the computer, you need to systematic update the software, no? So window always say update. So now, see, maybe you forgot to update because you have no time. So this situation happened, no? I don't know. Okay, so now I want to solve another kind of equation that contain one sophisticated weird number que es E. Suppose E, this is example 9. Example 9. Example 9 is E 3 minus 6 equal E to the third power raised to the minus 6. Wow. Entonces I need to understand who is E. Who is E? E is the famous mathematical constant. So in mathematics, there are several constants, very, very famous. The most popular is in geometry pi. Okay, it's a irrational number, right? This is a symbolic way to indicate, but the approximation is 3.14, 16, 5, something, bam, bam, bam. This is irrational. And the irrational number contain infinitely non-repeated decimal numbers. So now there are no reason or there are no possibility to express like a fraction. This is the idea behind irrational. Irrational. And E is another example of the irrational. Okay, I want to explain the idea behind this. The definition of the E is definition you in mathematics you put the column equal, and this is called a definition. There's a difference between equal alone is equal and there's a definition. Is, you know, a limited, but you don't know very well this operation because this operation is explained in calculus, but it's easy to understand. So when the M is a huge number of the one expression is 1 plus 1 over M raised to the M power, this is E. So to explain that, you don't know very well limit, but it's easy, intuitive idea. Look. Suppose that the expression is, you delete the word limit, and you put 1 plus 1 over M raised to the M power, and you increasing M, 1, 2, 3, 4, 5,000, 1 million, 10 million, and let me explain what magically happened. Yeah, same power goes from me. Okay, wow. Well, I have no idea. And you go out and get in again and click in the link and same situation happen. Well, don't interrupt me anymore, guys. Sorry. The majority of the students is here with me. Okay, let me try to explain this idea. Let me try to share one spreadsheet Excel calculator to explain that part. Look. Euler number, Excel. Do you see Excel? Do you see or no?
Yes.
Yes or no? Answer me.
Yes.
Okay. Now I create this spreadsheet because it's too long. Mathematicians doing that. Well, no long is yeah, it's long. It's long. I copy here a number 1, 2, 3 consecutive number. Y I evaluate this function in 1, and 2, and 3. And you see it's 2 point something, no? 2.6, 2. So I continue, look, wow. I continue to, yeah, I'm boring one moment to the 1051 something. Yeah, I stop in 51. But we can continue. We can continue. For example, let me copy that. Entonces, this is converged, approached 2.71 something, no? And entonces now to see more clear, I create in this spreadsheet one graphic. Boom! Look at that. One graph. In the x-axis, I have the number, no? 200, 400, 600, 800, 1000, 1200. And you see the numerical value of the limit when the n increasing forever. I guess it's synonymous to say approach to infinity. Try to stabilize state and one, this is not exactly flat, but increasing too slow to the one number que es e. And so I copy here the picture of the e I found in net. And you see we have infinity. Wow. So you don't need to memorize this, but at least you know, because in the next section we are working with the e. Okay, so you need to be aware who is e. Clear the idea of the e? Not too much, eh? But it's the thing you need to know so far. Okay, e, yes. Okay, now let's solve a couple of equations. Yes, you know who is e. So as I recap, e is a rational number, is a mathematical constant, famous, and we are using frequently in this chapter. Okay, so now we are doing exactly the same. Let me try to share one more time the whiteboard. Exactly. Okay, cool. There you go. Whiteboard. Do you see my whiteboard?
Yes.
Okay, now again, we apply the property of the exponent. This stays the same, I don't touch, but this not. This multiplication is e to the minus 3x. Now again, we have the same base case e. It's weird, but it's the same. Therefore, the exponent is the same. Let me try to solve for x. Maybe I move minus x to the right. Maybe. There are many ways to do that. Minus 3x plus x. 3 is equal minus 2x divided by negative 2 both sides. X is equal minus 3 over 2 is the answer. Exponential equation. This is easy. Look like easy, right? Or no? Yes or no?
Yes.
Yes. One more similar, and that's it. Example 10. 10 example we are doing. In the review bracket, we are doing more example. Suppose this. Entonces, the question of the what is the common base es obvio, que es e. Entonces, the only new thing I need to do is apply the rule of the exponent, no? Well, in this case, I don't touch this. I don't touch it. I just bring down 1. However, it is because of reciprocal. I know very well the reciprocal is negative 4. So you change the sign of the raised to the x plus 1. Now e to the x minus 1 is equal multiplication. The exponent is e to the minus 4 parenthesis x plus 1. Now ready. Two exponentials, same base, the exponent is the same. X minus 1 is equal minus 4 parenthesis x plus 1, and we have linear equation. You solve it in 5 seconds. X minus 1 equal, this is minus, I forgot, is minus 4x minus 4. Okay, so I move minus 4x to the right. X plus 4x is equal minus 4 plus 1. This is 5x is minus 3 divided by 5 both sides. X is equal to minus 3 over 5. Final answer. Do you feel strong in that part?
Yes.
Okay, cool. Now, to the motivation of the next section, suppose I have this exponential equation. 2 to the x equal 3. Wow, professor. This is impossible. Find one common base. And the answer is yes, you're right. It's impossible. Because 2 is 2. But 3 is impossible. Discover one exponent using base 2. So this is no common base. No common base. No common base. And we have no solution. Yeah, we have solution. Of course, we use a new idea. Use a new idea I want to study. I promise that when you study the new idea now, the first exponential equation that we're solving is this. Okay? And remember that in the last class, I say you, okay, you need to bring so far the calculator. Everyone bring the calculator today or no? Scientific calculator. Everyone bring me. Come on. One by one. I want que, a ver, Michael dice yes, Anika dice yes, Apolinario dice yes, who more dice yes? Come on, Yasmin, Sofia dice yes. Okay, I need everyone so far. Today maybe no too strictly. Today maybe, I don't know, depending the time. But you need scientific calculator. Because we are working with the special functions that we cannot compute it by hand. It's no by hand. 3 times 3, 3 times 3, 9. No, no. Calculator, scientific calculator. No, no Sedano supermarket calculator. Okay, no. Scientific, Karen, scientific, right. Stephanie, Caleb, Emily, Sofía, Elsa, you bring or no?
No.
No, why no?
Sorry. I'm going to wait today.
Yeah, really. But next class mandatory, because if you don't bring calculator next time, you lost the information for the calculator. Okay, I can do online using my virtual calculator, but this is not the same. So now we need to interchange information. No, I get the answer 4.5. But to say everyone get 4.5 in your own calculator. Okay. Okay, now let's try. Let's try to introduce a new topic to solving this equation. And after we see applications in the real life, in what moment we're using and what problem we're using this. Okay, so the thing we want to study now is a logarithmic function. Wow. Logarithmic functions. I put in plural, no? Because it's a family of the function. Entonces, by definition, the logarithmic function is the inverse function of exponential. Wow. So we studied in detail exponential function last time. And we studied in detail the inverse function. So that we are doing backward in opposite direction. No? That's the idea. No? Let me explain in detail. So the exponential you very well know. F of x equal a to the x power. This is the famous exponential. Okay. Now I try to find the inverse. How? Well, you replace f of x for y, because you know very well that y and f of x is the same, always. But the only advantage of this notation is function notation, okay? You know, was useful for the transformation to understand y in a set, x in a set. But it's the same. Same stupid thing. Now you replace. Okay, this is also exponential. I don't touch. Now, crucial moment. So you want to find the inverse, remember, you interchange x and y. This is the key idea. This is the most important moment. And you copy x equal a to the y. But the disadvantage, this already is the inverse. However, es que es no en explicit, es implicit. Remember, implicit means, implicit form, es que y is no isolated, unfortunately not clear. Now I need explicit, and explicit is clear, therefore y is alone, isolated. So now the notation that we using, and you need to understand, is you copy the name of the function. Look, this is the name of the function, and we're using 3 letters, log. Log, okay, you open parentheses because it's like a function notation, no? The function notation, you copy the name of the function, f, and you copy x alone. No, you put the parenthesis to indicate that this is the argument of the function in which the x value is the belong to the domain. So similar situation happen. You put log, your specification now x here, because this x, the same x is this. But you put a small number here, a small to a specification the base. Okay? This is the logarithmic function. Maybe you don't understand anything now, but I want to put several examples because I would like can you understand very, very, very well the interpretation for the logarithm. Very, very well the interpretation without calculator. Today, basically, is the day to get the intuitive idea for the logarithm. What means that? What is the interpretation? So I propose to interpretation that I propose put together the exponential and the logarithm because you are familiar, no, with the exponential. So this is an exponential statement. Okay, you are familiar. Versus the new statement that I am studying now, que es logarithmic statement. For sure, we are doing conversion in both directions. We are doing conversion from exponential to logarithm, or from logarithm to exponential. You need to understand this, and we use it frequently in the chapter. Suppose elementary example. Suppose 2 to the 5th power is 32. Okay, I saw before. How you change this to logarithm? Well, okay, you put the log, get the name of this function. So the teacher explained me, can you put a small number here que represent the base? Well, I can see que the base is 2, no? And the exponential, entonces it's the same base, 2, 2, 2. Entonces you have one number inside the argument, and we have one answer. I need to remember que the answer is always the exponent. So the answer is 5. And the number que stay is 32 inside the argument. So what is the interpretation? What information give me the logarithm? Well, the logarithm give me, when you put in calculator, what on it, in this case 5, okay, you need to in this case 2 in order to get 32. So we're doing Bauer, completely Bauer. And the exponential, we have the base, just give it. The exponent is given, and you need the result of the exponential. And the logarithm, no. And the logarithm is given the base, 2 in this case, you obtain the result que you obtain of the exponential, que es 32 inside the argument, you put 32 here, and you need to find the exponent, the answer. Keep in mind, the answer of the logarithm is the exponent, right? Another example, suppose 3 to the 4 power is 81, because it's multiplication for 3, no? 3 times 3 times 3 times 3. It's obvious because 3 times 3 is 9. I know very well that 9 times 9 is 31, no? Okay, without calculator. Now, you want to change to the logarithm statement, you put log. Entonces, I ask myself, who is the base? Oh, the base is 3. Open parenthesis. Who is the exponent? The exponent is 4. And the exponential statement. And the argument is 81. So when you compute on the calculator, you see, no, maybe today, logarithm base 3 of 81, the answer is 4. Because it's the exponent que is necessary to allocate in the exponent of the base 3 in order to get 81. Okay, in general, we can generalize. Okay, we have, for example, base. You have base. You have exponent. Okay, and you get the result. This is a typical format of the exponential statement. However, when you change to the logarithm statement, you put log, you put a small number here that represents the base, you open the parenthesis, and the answer que offer is exponent, you know, and the number inside is the result of the hypothetical exponential we are doing before. And guys, by the way, this statement is completely interchange, so you navigate in this direction or in this direction. We are doing several examples today to do compute exponential, as a conversion from exponential to logarithmic, and compute logarithm without calculator. Okay. For example, this is easy, extremely easy to understand base 10. Base 10. Because 10 is nice. That is a reason that we study that base 10 is standard. In the calculator, we have 2 standard. One is 10. But no, I don't care now. Forget about calculator for a moment. Standard base, I guess call it common. Common base. Entonces, now suppose logarithm base 10 of 100. No idea. And lost. I don't understand very well logarithm so far. Okay, I need to find, the teachers say que the answer of the logarithm is the exponent. So I need to find, in my mind, one exponent que you raise to the 10, get the base, give me 100. Do you see what is that or no? No?
10.
10. No, because 10 to the 10 is a huge number. No. So I need, es 2, obviously, es 2. Es 2, because 10 square, que es 10 times 10, is 100, correct? Intuition. Suppose que I don't know. Professor, I don't see that. Okay, no problem. Now, you don't know, always que you don't know something in algebra, you put x, and you change this logarithm statement to exponential, and you indicate always in the test. You put an arrow, and you put to exponential, Everyone understand? Can you change the logarithm statement to the exponential? I asked by myself, what's the base? Oh, the base is 10. Raised to the one exponent. What is the base? The exponent. The exponent is the thing I don't know. It's the thing I try to find. It's equal 100. So this statement is 100% equivalent to this statement. The only thing it changed is the shape. It's another form, but it's the same algebraical equivalent. Now I know we face now the solution of the one exponential equation. And I try to find the common base, que obviously is 10. And I know que 100 is 10 squared. Therefore, same exponential, same exponent, the answer is 2. Bam! Do you understand this or no?
Yes.
Do you understand a little bit the intuitive idea of the logarithm or not yet?
Yes.
Okay, let me play a game. I put an example and you try to guess in without calculator. It's using intuition, using a conversion to exponential, maybe, I don't know. Suppose logarithm base 10 of 1000. What is this? Come on, competition. Come on, guy. Come on, Miss Love, are you there? 10. Michael says 10. Everyone is agree with Michael? 10, right. 10.
3.
Apolinario dice 10. What? Another opinion. I got 10. Wow. Sophia 10. Wow. What happened with this class?
Is 3?
Absolutely. Absolutely que 3. Let me solve it in a different way. Pay attention. Look, suppose that I have no idea. Totally lost. I put x. I change to exponential. The base is 10. The exponent, I have no idea. 1000. And 1000, I know very well que 10 times 10 times 10, no? Or 10 to the third power. Yes or no? Therefore, one more time, we have two exponentials, same base, x3. Everyone understand this or no? I don't finish. I have a lot of competition. Try to understand this, coño. Look, logarithm base 10 of 1 million. 1, 2, 3, 4, 6, 0. What is that? Yes. Yes is not the answer. The question is not yes or no. What is the logarithm base 10 of 1 million? 6,
5.
right? No, 6.
6.
Let me try. It's 6. Suppose I have no idea. Okay, I copy 10 to the x, I change to exponential, and this is 10 to the 6th power because we have 1, 2, 3, 4, 5. Okay, look, it's 1, 2, 3, 4, 5, 6. 10 to the 6th power is 1 million, ¿no? Es obvio que x es 6. Entonces, sí, profesor. Wow. Si you have 2, 0, es 2. Si you have 3, 0, es 3. Si you have 6, 0, is 6. Bueno, this happened in the base 10, this partner. In other base, no. Of course, no. But I want to complicate your life, and you, let me try to continue playing a game. Suppose logarithm of base 10 of 10. What is the answer?
1.
Exactly. Very well. How do you know? Es 1. Because what is the exponent that you need to raise 10 in order to get 10 is obviously 1, no? And this is a super important property. So logarithm of the any base and the number inside the argument is coincident with the base is 1. Example, logarithm of base 3 of 3 is 1. Logarithm of base 5 of 5 is 1. Do you understand this idea?
Yes.
Okay. Now let's continue with the logarithm of base 10. Sophia said, yes, I understand. Thinking now. Logarithm of base 10 of 1. Boom. Today is the day to understand the meaning of the logarithmic functions. So you are strong, so you understand. I hear, when I teach that, I hear the students in another class, okay, say, I never understand logarithmic. This is too complicated for me. I don't understand why, but it's just new idea, but you need to adapt your brain to the new idea. No? This is the education. No? Okay, now what about this? So suppose that I am lost. You put x, because maybe when you change to exponential, maybe it's more clear for you to see that. So you have 10 to the exponent, I have no idea, equal 1. You can find common base. Well, yeah, you can. You can, because I need to remember okay, any number raised to the 0 power is 1. Okay, any number. It doesn't matter que es 10 or 3 or es. Entonces, this is equivalent to say 10 to the 0 power. Therefore, same base, the answer then is x equals 0. Oh, professor, then this is valid for any logarithm. Yes, it's another fantastic property. This is one fantastic property when there are coincidence in between this number and this number. And another fantastic property is logarithm of the any base 3, 5, 20, whatever, of 1 with the argument is 1 is 0. Is 0. Logarithm of 1 is 0. Right? After we verification everything in the calculator. After, but not now. Do you understand? Do you follow me? Keep in mind, logarithm of the 1 is always 0. We're using this property, not every day, but we use it. Now I want to complicate more this. Logarithm of 10. I continue with the 10. Professor, what is the reason you are using 10, 10, 10, 10? Well, because 10 is easy to understand by hand. Of the 0.1. What is that? What is that? 0.1 logarithm. And logarithm as set fraction? Yeah, logarithm as set fraction. I want to explain in detail now. Logarithm as set fractions. Somebody have idea or no? Come on, play again. Play a game of the logarithm. Come on. Demari, Sofia, Yamin. We have 2 Sofia, no? Adolfi and Kaba. Stephanie, Bautista, Caleb, Gloria, Dalia, Fernando, Daniel, Michael, Eric Troncoso. Wow, Eric, you need to improve in this test. Okay, Miss Love, are you there? Or you are sleeping? No, I suppose you are sleeping. Miss Love, Grace, Love, Sarah, Sofia. We have 3 Sofia. Sofia, Sarah, Sofia Adolfi, and Sofia Capa. Anika, Apolinario, you are lost. Come on, guy, say something. You know?
I can't see the blackboard, and I don't know if it's just me, but the blackboard completely disappeared for me. Can you tell me what the problem is?
You don't see the whiteboard?
Yeah, I don't see it at all.
Now?
Yes, I do. Thank you. I'm gonna go solve it now.
Okay, so now try. Try to find logarithm base 10 of 0.1. Nobody have idea. Well, me too. So I try to find the systematic. -1. Very well, Anika. -1, -1, -1, -1. The answer is -1. And remember, -1, this is exponent, it's reciprocal. Yes or no? -1, keep in mind. I know that it's hard for you to understand negative exponent. Sorry. Okay, this you change to exponential. The base is so big as 10. The exponent, no idea. And this is equal 0.1. And 0.1 is present in fraction is 1/10. It is present using negative exponent is 10 to the -1. But I want to express it that way because I need to express it both sides using the common base, que es 10. Therefore, clear case x is equal to -1. Do you see or no? Apolinar, you see now? Yes. And what about logarithm base 10 again of 0.01? Wow. Wow, wow, wow. What is that? Confusing. I don't understand anything. Es negative 2. Super cool. Es negative 2. And logarithm base 10 of 0.001. So one more zero after the decimal point. It's -3 and so on. Let me prove. Suppose I have no idea. I put x. I convert to exponential statement. Extend to the x is equal 1/100. Entonces, this is like 1/10 squared. Reciprocal is 10 to the -2. Therefore, same exponential is -2. X equal -2. Okay, do you understand very well? Okay, cool. Cool. Entonces, now, well, I bring another example. No base 10 anymore. No, anymore, no, for a moment. I bring another example and you help me. Today is the day to understand the logarithm using intuition idea. Intuition. Logarithm base 4 of 64. Remember, what is the question can you ask by yourself? I need to find exponent. I need to find one exponent, question mark. Okay, when you raise 4 to this number, give me 64. Okay? Exactly. Very well. That's 3. Very, very well. Who said that?
Elsa.
Elsa. It's 3. Suppose I don't know. Suppose I don't know. Okay, to see more clear, you change to exponential. The base is 4. The exponent, I have no idea, equals 64. And this is now, this is logarithmic equation. Okay, I am not familiar, no. However, I am a little bit familiar. The teacher explained me exponential equation. And the 64 is 4 to the 1 power is 4. 4 to the second power is 16, 4 times 4, no? And 4 to the third power is 64 because 16 times 4 again is 64. Therefore, this is 4 to the third power. Therefore, we have two exponentials, same base. Therefore, x is equal to 3. Cool? Cool. Yes. Suppose now I want to complicate a little bit your life now. Logarithm base 4 of, no, base 3. Base 3. No, base 5. Let me copy base 5. Base 5 of 1/125. Wow. This is really weird. I don't know. Choo. So now, this is important. Keep in mind. The base is 5. 5 is a number bigger than 1. And inside the argument, we have 1/25 as a fraction, gets less than 1. You see, for example, in the example 1, I call example 1 this. I call example 2 this. In example 1, the base is 4 is greater than 1, and 64 is the number inside the argument is also greater than 1. Oh, this is very, very, very compatible. So it's the same situation. That is a reason we get a positive solution. However, when you see a contradiction, the base is a number greater than 1, and the number inside the argument is less than 1, it's because in one moment I need to flip it, yes or no? So to flip it, that we need negative exponent, right? Do you understand this idea?
Yes.
Keep in mind, of course, yeah, flip it, yeah. Of course, today I explained the intuitive idea, but you put it in the calculator and you get the answer, and that's it. But you need to know the intuitive idea. Okay, suppose those I have no idea. You have idea or you have no idea? What's the answer of this? So you have no idea, you put x, you convert to exponential to see more clear. The base is 5 to exponent I don't know equal 1 over 125. Entonces now I change my problem from exponential logarithmic, sorry, to exponential. It's negative 3, super, it's negative 3. Yes, it's negative 3 because 125 is 5 to the third power and reciprocal is negative exponent. It's the most important idea that you need to remember. Therefore, we have a common base, the solution is negative 3. But I anticipate this answer to analyze this. See, the base is 5 is greater than 1, and the number inside the argument is less than 1. So I anticipate that we have negative exponent, and the reason is because in one moment I need to flip it. Okay, by the way, it's this moment, no? I flip it. Okay. Okay, let me try now another example. Logarithm base 3 of 81. Okay, I lost. I don't understand very well. Okay, but I analyzed the base is 3 is greater than 1, and 81 is also greater than 1. So there are no contradiction. Nice. Therefore, we expect positive number here. But I have no idea. You change to the exponential, the base is 3, the exponent I don't know, equal 81, but 81, 3 is 3, 3 to the second power is 9, 3 to the third power is 27, multiplication by 3 by 3 by 3, 3 to the fourth power is 81. This is equivalent 3 to the fourth power, therefore same exponential function and same base, therefore the exponent is the same, x equals 4. And we predict that because it's the same, greater than 1, greater than 1. See, one is greater than 1 and another less than 1, so we have contradiction and you flip it. Suppose the last example, before start strictly the logarithmic function, because we are doing now just intuition. Suppose logarithm base 1/2 of 4. What do you expect? You expect positive solution or negative solution?
Negative.
Exactly, because 1/2 is less than 1 and 4 is greater than 1. You see contradiction. So in one moment of the game, definitely I need to flip. Therefore, negative exponent, Sophia. Suppose I wanted to find exactly the value, I convert to exponential because my mind, you know, is adapted to understand much better the exponential equation. Logarithm is no clear for me. So I copy the equivalence statement in exponential form. The base is 1/2, the exponent is x, okay, I don't know, and the answer is 4. But I need to solve this using common base. And using common base, well, I don't know. 1/2 is 2 to the negative 1 exponent, no? reciprocal. And 4 is 2 to the second. So you copy 2 to the negative 1 raised to the x equal 2 to the second. One more time, you apply the property of the exponent multiplication. 2 to the minus x is equal to the second power. Now we have two exponential with the same base, therefore minus x is equal to, therefore x equal minus 2. Exactly, we predict negative because we have a contradiction between the base and the argument. One is less, also it's completely opposite, no? One is less than, another is greater. Okay. So far, everyone follow me? So far, everyone follow me? Good.
Yes,
Yes or no? Follow me?
Yes.
Question?
I said yes.
Yes, cool. Now we study formally. Now the logarithmic function, exactly the same we are doing before. In the, remember, exponential, logarithmic, secular. Look, let me try to bring one rectangular coordinate system. Yes, here, over there. No. Okay. Maybe here. Okay, there you go. There you go. Bueno, professor, you say que we study a property for the logarithm. Let me try. Pero I know que logarithmic function is inverse of the exponential. Let me start doing the exponential. Suppose que I select one easy base to understand. Suppose base 2. Suppose this exponential y equal 2 to the x power. Yeah, I do quickly. Remember, I discovered last class que we have a common point, universal point, que es 0,1. 1 is 2, 2 is 4, because 2 to the second, and 3 is 8, que es completely out. And negative 1 is 2 to the negative 1, que es half. It's a half of this segment, and negative 2 is a half of the half. And you say que es asymptotically, no? Asymptotically, some y curve of the exponential that we studied last class look like that. Boom, this is 2 to the x. Entonces the professor say we have horizontal asymptote at y equals 0, que es coincident with the x-axis. This is the horizontal asymptote, coincident with the line y equals 0. So that continue, pero you know, approach it, pero never touch. Okay, this is exponential. Now, it's easy to do the graph of the logarithm because I take advantage, base 2, of course, the same base of x. Let's do the graph of this. That point was 0,1. And the logarithm, remember, is the inverse, and the inverse interchange x and y. Therefore, the only thing you should do is interchange. Now, the point and the logarithm is 1,0. And this is universal, because you know very well the logarithm of the any base, not necessarily 2, of 1 is 0. But the point 1,0 belongs to the any graph of the logarithm. It's a universal. And suppose now logarithm base 2 of 2 gets second property, 1. Entonces, pero no, because I take that point in the exponential, que es 1,2, and the logarithm would be 2,1. Bang. And this point was 2,4, and the logarithm would be 4,2. Entonces, the logarithm look like a little bit like that. It's a logarithm of base 2 of x in general. What happened with that part? I don't know. That part is confusing for me. Well, no, it's not confusing because, for example, that point is the point negative 1 comma half. And the logarithm would be half comma negative 1. And half is here, and between 0 and 1, negative 1. That point is the continuation, guys. After I want to show you in Desmos, super clear. This point is the point half comma negative 1. And likewise, 1/4, 1/4, negative 2, and so on. No? Entonces, this is continue like that. Bam, 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 bam. However, I can see that the graph of the logarithmic contain a vertical asymptote at x equals 0. This is vertical asymptote at x equals 0. Que es analogous somehow to the horizontal asymptote in the exponential, que es y0. But important, crucial moment. The graph in the black color is the graphic I want to show you. It's the graphic I want to analyze. Okay, look. Suppose I ask you, look in the graph, no mathematical. What is the domain of the logarithm? Domain and range. Look in the graph, look at the graph. Remember how you find domain and range? Domain first, after range. How you find the domain? You take the curve, what curve? The black. And you project it onto the x-axis. And you get the value, the set of the x value que that function is defined. Therefore, this is our domain. What do you think about domain? No idea? This is the logarithmic. The exponential, I studied last time. Domain and range. Yeah, I discovered last time that this is already a number, an exponential, and the range is always 0 or infinity. An exponential. Look, so you are doing, for example, the projection of the red one curve, get exponential, onto the x-axis already a number in both directions, positive infinity, negative infinity, no problema. However, in the y-axis, we have only projection in the positive part. Because in the negative part here, over there, we have no exponential. No. However, in the logarithm is the same, well, no, completely opposite because it's the inverse function. Now the domain is this, coincident with this. And the range is coincident with this. Let me try to see this is coincident with this. Let me try to see graphically at least. Well, in the logarithmic function, get the black color curve, we have only, this is asymptotically. Asymptotical means que approach pero never touch. When you project any point onto the x-axis, you see only the projection is the positive part. I don't see logarithm in the negative part. That is a reason que the domain is from 0 to infinity. No include 0. No include 0. So let me take advantage of that moment to say something important. Logarithm. It doesn't matter the base of the negative number do not exist. Undefined. Logarithm. It doesn't matter the base of 0 undefined. So you try, when we working with the calculator, you put negative number inside the argument of the logarithm, automatically you see error out of the domain. The calculator offers different matrices depending on the calculator. And 0 is similar, undefined. So we have only solution in the logarithm in positive and no 0. Those are non-negative. That's the idea, non-negative. Non-negative. Do you understand very well this idea? Okay,
Yes.
Let me try to take advantage also to see another property. This is a one-to-one function, it's obvious. That is the reason que es invertible. that the inverse of the exponential is the logarithm, and the inverse of the logarithm is exponential. So that is a reason that we can interchange in both forms. What is the exponent set of the logarithmic function? It's this point. It's the famous point 1,0. By the way, this is universal. And the word universal is because logarithm of 1, regardless, the base is always 0. And why is it? No, we have no. Because the curve and black color never touch or cross the wax. No. And obviously this is symmetric with the identity function. Remember the idea that we discussed at the beginning of the chapter, no? Because we have the line that represent the line y equal x, que is the identity function, and the exponential, que is the red color, and the logarithm, que is the black color, are symmetric with respect to that. Okay, one more information. Okay. So now, domain and range is clear. Typical points, suppose in the test, I guarantee you, okay, we have one question to do the graph of the exponential, and another question doing the graph of the logarithmic. So 2 questions graphically. Of course, we can do it using decimal, no, but you need to do a little bit table to understand this. So now the typical point, okay, we are using typical points we're using to plot any logarithmic function is 1,0. Okay, this is totally impressionable. This point is universal point. And another, suppose hypothetically, suppose that I have logarithm base. Let me try to take advantage the meaning of the class to explain 2 examples of this. Let me try to clear. I bring 2 rectangular coordinate system. Let me make copy, and paste. Cool. Suppose in the test is given this information. I need to do the graph of the logarithm. Suppose base 3 of x. And here, logarithm base 1/2. No parentheses, sorry. 1/2 is the base of x. Okay, y equal or f of x, either way. Let's start for the first one. Okay, remember the typical point universal, 1,0, bang. And here, likewise, bang, any family of the exponential, the logarithmic function passing through this point is universal, regardless the number of the bases, 3, 5, 4, or fraction, 1/2, 1/3, 1/4. But the other point, okay, is 3,1. Yes, because I know that when the number inside the argument is equal, this is 1. And the other after that is 3 to the second power, get 9, it's completely out. So you see, it look like that. And that part is like that. How, for example, you can see logarithm of base 3 of 1/3 is -1. So 1/3 is you take that segment between 0 and 1 divided by 3, I suppose here. So this is the point. So you know, it's enough. You understand it look like that. And don't forget to write the vertical axis of any graph of the logarithmic function has. Okay, and you they're not clear to see 3,1, 1,0, at least 3 points. You emphasize 1/3, -1. Cool. Let's do the second. The second is a little bit different. They behave because because the base is less than 1. Just completely opposite signs, and now it's decreasing. So we plot the same point, 1,0. This is universal, cool. But suppose I compute logarithm of base 1/2 of 2. Oh, it's obvious que negative 1. Yes or no? Do you see? Why? Because 2 is a reciprocal 1/2. Entonces 2, negative 1. Oh, is here. That point is the point. 2, negative 1. And logarithm 1/2, 1/2. Oh, I know. The professor explained me when the coincidence in between the numbers is positive 1. Entonces this is 1/2, que is here, positive 1. This point is the point, 1/2, 1. This the logarithm is different, look like decreasing, like that. Oh, I try to do my best. Ooh. Okay, this is logarithm base 1/2 of x function. And don't forget one more time to draw the vertical asymptote on the y-axis. Okay, this is vertical asymptote at x equals 0. It's classical, vertical asymptote at x equals 0. Everything is clear so far? So now, Friday, everyone bring the calculator, because we are working with this. We know the conceptual idea for the logarithmic. Now we are using, okay? And, you know, sometimes we can compute it by hand, like this elementary example, but not always. Not always. So now we need calculator. Cool? Clear?
Yes.
Okay. So now I gotta go. Do you see my face?
Yes.
Bye-bye, guys. See you.
Bye, Professor. See you.